Welcome back. In the previous class, we discussed about the operations on single random variables. Okay, so now in this class, we are going to discuss the operations on multiple random variables. Along with, we will see what are Gaussian random variables, okay, and what are different operations and linear transformations on Gaussian random variables. So what are multiple random variables? So actually, if variable will happen in the future, so generally it is considered as random variable. So till now we have discussed about one or two random variables, but in many applications we have to deal with more than two random variables. Okay, so for example, the noise affecting the RGB channels, okay, red, green and blue, okay, primary channels, okay, primary color channels. Color video may be represented by three random variables. So that is the necessary. That is why it is necessary to learn about the operations of multiple random variables. So not only this thing, whenever, okay, so we have to study about the communications, okay, many signals have been transmitted through communication channels, okay, so many types of noise can enter the channels, so okay, those also can be modified into random variables. So noise mostly it is represented as Gaussian noise, so that is why it is necessary to study about multiple random variables along with Gaussian random variables. So in such situations, it is convenient to define the vector valued random variables where each component of the vector is a random variable. Okay, so when we extend the operation for n random variables, okay, so then mostly we represent that random variables are vector valued random variables. So among that, each and every vector is nothing but a random variable. So let us see what is the expected value of a function of random variables. So in the previous class also we discussed this. Okay, let us recall this once again. Suppose z equal to g of x comma y is a function of continuous random variables x and y. Then the expected value of z is given by using this formula. So E of z. So expectation of z equal to E of g of xy, which is nothing but the function, which is equal to integral minus infinity to infinity z fz of z dz. Okay, so here z is the expectation. Okay, z is the random variable. Okay, so integral minus infinity to infinity z fz of z dz is the expectation of the z. Okay, so fz of z is nothing but the probability density function of the z. So since here we are discussing about two random variables, okay, so which are jointly connected. So this expression is again can be written as integral minus infinity to infinity, integral minus infinity to infinity. Why we have taken two integrals here? Because here x and y are two random variables, and that too they are jointly distributed. Okay, so they are jointly connected. So g of x comma y fxy of xy dx dy. So g of xy is function. Okay, fxy of xy is the probability density function of jointly. Okay, joint probability density function of both x and y. Okay, so since here we have taken two random variables, two integrals we have taken. So if z equal to g of xy is a function of discrete random variables, so we can similarly show that expectation of z, which is nothing but the expectation of g of x comma y, is equal to, so sigma x comma y always subset to the rx and ry. Okay, so rx and ry are nothing but the integers. Okay, set of integers. Okay, so sigma g of x comma y pxy xy. So g of xy is function, pxy of xy is the probability mass function of both x and y. So here we have an example problem. Okay, so here we are going to determine, okay, the joint expectation of g of x. Okay, the joint probability density function of two random variables x and y is given by fxy of xy, which is equal to 1 by 4 xy. So this probability, okay, joint probability density function lies between 0 and 2 values. Okay, 0 is less than, x is less than or equal to 2. Similarly, 0 is less than or equal to, y is less than or equal to 2. Okay, so here x and y are distributed along the values 0 and 2. And this density function will be 0 otherwise. So if it is less than 0 or greater than 2, so those values will be 0. So find the joint expectation of g of xy. So the function value here we have taken is x square y. So now expectation of g of x comma y equal to, so what is the function given here? X square y. So e of x square y. So since here it is joint probability density function, okay, so we have to take two integrals, minus infinity to infinity, minus infinity to infinity, g of xy, fxy of xy, dx, dy. Okay, and what are the limits we have now? So x is distributed over 0 and 2. Similarly, y is distributed over 0 and 2. So because they are jointly distributed random variables. Okay, so that is the reason we have taken the limits for both integrals as integral 0 to 2 and integral 0 to 2. So g of x value is x square y and fxy of xy is 1 by 4 xy dx and dy. So here we have x square and x. So x square into x is x cube. Okay, and y another y into y is y square. So here we are going to separate the limits for both x and y. So 1 by 4 equal to, so since 1 by 4 is constant, we are writing it outside of the integration. Okay, so 0 to 2 x cube dx. Okay, integral 0 to 2 y square dx. So we just separated the integrals for both x and y. So now what is the integral value of 0 to 2 x cube dx? So x power 4 by 4. Okay, so and what is the integral value of integral 0 to 2 y square dy? Y cube by 3. Okay, so the limits are over 0 and 2. So 1 by 4 into, so actually when we apply the limits here, what will happen now? X4 by 4. Okay, 2 power 4 by 4. Okay, so 0 power 4. Okay, actually we have to first substitute the upper limit, which is nothing but the 2 x power 4. Okay, so minus 0 power 4. So 0 power anything is nothing but 0. So we just eliminated that 4. Similarly, for y cube by 3. That means 2 cube by 3 minus 0 cube by 3. Okay, 0 by anything is nothing but 0. So we just eliminate the lower limits. Okay, so 1 by 4 into 2 power 4 by 4 into 2 cube by 3. So on the simplification, we will be getting the value, the expectation. Okay, the joint expectation of the function g of xy is 8 by 3. So next coming to the joint moments of random variables. Okay, so previously we have observed how to find the expectation of function g of xy. Okay, so that is nothing but the first moment. Okay, first moment, which is nothing but the mean. Expectation is nothing but the mean. So just recall. Previously, we have studied about the expectation of random variable, okay, single random variable. Okay, expectation in the sense, which is nothing but the mean. Mean is nothing but the first moment. Okay, so here we are going to study about the joint moments of random variables for the set. Okay, when we extend. Okay, So the random variables concept to n and m number of values. Okay. So joint moment provide the summary description of the two random variables. Okay. For two continuous random variables x and y, the joint moment of order m plus n is defined as. So here we are extending this concept to for m values of x and n values of y. Okay. So in such case, the joint moment, okay, which is nothing but the expectation of x power m y power n is defined as integral minus infinity to infinity and integral minus infinity to infinity x power n y power n fxy of xy dx dy. So this is the central moment, okay, so of x power m and y power n. So similarly, if m equal to 1 and n equal to 1, what we'll be getting? We'll be getting joint central moment of the order n plus n. Okay. So and the joint, sorry. So this is the joint central moment of the order m plus n. Okay. So when both m equal to n and n equal to 1. Okay. So m equal to n 1, n equal to 1. So in such case, we will be getting the second central moment of the joint random variables. Okay. So on joint central moment of the r m plus n is defined as, okay, so for nth case and mth case. Okay. So e of x minus mu x whole power m. Okay. So this is the moment. Okay. So this is the central moment. Okay. So central moment in the sense we have to subtract the expectation, okay, which is nothing but the mean from the random variable. So expectation of x minus mu x for nth order, y minus mu y for nth order is equal to minus integral infinity to infinity, another integral minus infinity to infinity, x minus mu x whole power m, y minus mu y whole power n fxy of xy dx dy. So this is the joint central moment of the order m plus n. So here the joint moment, okay, of the order m plus n. Okay, did you understand? So this is the joint moment, whereas this is the joint central moment. So if x and y are discrete random variables, then the joint expectation, okay, or the moment of order m and n is defined as expectation of x power m, y power n, which is equal to sigma x comma y, always it is a subset of r x y, okay, which is nothing but the set of integers, okay, and sigma x power m, y power n, pxy of xy. So pxy of xy is nothing but the probability mass function of joint probability mass function of both random variables x and y. So and the central moment, okay, so of discrete random variables of order m and n is defined as expectation of x minus mu x whole power m, y minus mu y whole power n, which is equal to x comma y, always is the subset of r x y, sigma x minus mu x whole power m, y minus mu y whole power n, pxy of xy. Okay, the first one is the moment, second one is the central moment. So if m equal to n and n equal to 1, okay, if m and n are equal to 1, so we have the second order moment of the random variable x and y, which is given as, so e of xy, because here m and n values are 1. So integral minus infinity to infinity, minus infinity to infinity over the integral, okay. So xy fxy of xy dx dy. So if both x and y are continuous, so this formula is applicable. But what will happen when they are discrete? So we have to take the summation, okay. So using sigma, okay, of discrete random variables. So sigma xy, which is always the subset of r x comma y. Okay, xy, sigma xy, pxy of xy. Okay, so this is the second order moment. Okay, so like that. So based on the values, okay, power of the random variables will be getting second order moment, third order moment, so and so on. If x is if we are taking x power m value, that is nothing but the mth order moment. If we are taking y power m, it is nothing but the nth order moment. Since these are jointly connected, okay, so we have to take the joint connected moment as of the order m plus n. Next, coming to the covariance. So the covariance, okay, of two random variables x and y is defined by the formula covariance COV of xy equal to expectation of x minus mu x and expectation of y minus mu y. Okay, so this covariance is generally denoted by sigma xy square, sigma square x comma y. Okay, so equal to expectation of xy minus expectation of x. See, here we are multiplying these two values, okay, because they are jointly connected. So expectation of x into y, e of xy, okay, minus expectation of x into mu y, okay, minus e of x into mu y, minus mu x into e of y, okay, minus mu x e of y, minus mu x into minus mu x plus mu y. So e of xy. So e of x is nothing but the mu x, mean of x. So here we have written minus mu x into mu y. Similarly here minus mu x into e of y is nothing but the mean of y, mu y plus mu x mu y. Okay. So here these are nothing but e of xy minus 2 mu x mu y plus mu x mu y. So one can be subtracted from the other. Okay. So e of xy minus mu x mu y. So here covariance, okay, of two random variables which are jointly connected. So which is it is denoted by sigma square xy, which is equal to e of xy minus mu x into mu. Okay. Next, coming to the correlation coefficient. The correlation coefficient of two random variables are generally defined by the ratio of covariance by multiplying their standard deviation. Okay. So rho xy equal to covariance of x comma y by sigma x, okay, sigma y. So product of these two standard deviations. Okay. So when rho of xy is greater than 0, then xy are positively correlated. So its value will be positive and they are positively correlated. Okay. And if rho of xy is less than 0, x and y are negatively correlated. Okay. So the relation between those two random variables will be the negative integer. So rho of xy, if it is 0, then x and y are uncorrelated because there is no relation between them. So then only we will be getting the correlation coefficient as 0. And we have one more property which is nothing but the modulus of rho of xy is always less than or equal to 1. Okay. So let us prove this. So rho of xy equal to covariance of xy by sigma x into sigma y. Covariance can be written as e of x minus mu x, y minus mu y. Okay. So this is nothing but the expectation. Okay. Expectation of x minus mu x and y of y minus mu y. And sigma x and sigma y are nothing but the standard deviations. Okay. So which can be described as square root of e of x minus mu x whole square, e of minus mu y minus mu y whole square. So now take the modulus. So modulus value is applicable to the only numerator. Okay, because in the denominator it is already there is square value. So when we apply the modulus value for e of x minus mu x, y minus mu y, we will be getting modulus of e of x minus mu x, y minus mu y. So the modulus value can be written as square root of whole square. So that is why square root of e of x minus mu x whole square and square root of E of y minus mu y whole square. Because here we have taken separately, okay? Separately modulus for both E of x minus mu x and E of modulus of E of y minus mu y. So, since though they are separately connected, the square root is same. So here we can combine the square root and we can write this expression as square root of E of x minus mu x whole square into E of y minus mu y whole square. So if you observe this, both the expressions in the numerator and denominator are same. So they can get cancelled, which is equal to 1. So thus we have proved that the modulus value of correlation coefficient, okay, rho of xy is always less than or equal to 1 but not greater than 1. Next, uncorrelated random variables. Previously we discussed that, okay. So if the covariance is 0, two random variables are said to be uncorrelated. So covariance of xy is 0. So what will be getting? Exy minus mu x mu y equal to 0. Okay. So because here you can see the relation. Because see, covariance is 0. So sigma square xy will be 0. That means what we will be getting? E of xy minus mu x mu y equal to 0. So which can be also written as E of xy equal to mu x mu y. Okay. So therefore what we can write this? E of xy equal to, so mu x is nothing but the expectation of x. Uy is nothing but the expectation of y. So E of xy equal to E of x into Ey. Thus what did we understand? When the random variables are uncorrelated, then E of xy, expectation of x and y, is equal to the product of expectation of x and expectation of y. Next, coming to the topic of joint characteristic function. Okay, so joint characteristic function of two random variables x and y is defined by the expression phi of xy of omega 1 omega 2 equal to expectation of e power j omega 1 x plus j omega 2 y. So if x and y are two continuous random variables, then phi of xy of omega 1 omega 2 equal to integral minus infinity to infinity, integral minus infinity to infinity, fxy of xy e power j omega 1 x plus e power j omega 2 y dx dy. And so here fxy of x comma y, which is nothing but the joint probability density function, can be calculated by using the formula fxy of xy equal to 1 by 4 pi square integral minus infinity to infinity, integral minus infinity to infinity, phi xy of omega 1 omega 2 e power minus j omega 1, okay, minus j omega 2 d omega 1 d omega 2. Okay, so broadly if we observe this, so these are like Fourier and inverse Fourier transforms, okay, except there was sign change. Okay, so if x and y are discrete random variables, we can define the joint characteristic function in terms of the joint probability mass function as follows. So now if they are discrete values, phi xy of omega 1 omega 2 equal to sigma x comma y, which is always subset to the Rx and Ry, sigma p of xy x comma y e power j omega 1 x plus e power j omega 2 y. And coming to the properties of characteristic function, okay, so phi x of omega equal to phi xy of omega 0. That means when y equal to 0, if the random variable y is 0, okay, so then its characteristic function is similar to that of characteristic function of random variable x. Similarly, if y is 0, okay, the joint characteristic function of random variables x and y, okay, then the phi xy 0 comma omega is nothing but the characteristic function of simply y, phi y of omega. So, and phi xy of omega 1, omega 2, so values is nothing but the product of characteristic functions of x and y. So, this can be proved like this. Phi xy of omega 1, omega 2 equal to expectation of e power j omega 1 x plus e power j omega 2 y. So, e power, so when you separate this exponential value, okay, so expectation of e power j omega n x into e power j omega 2 y, okay. So, here we can write this as expectation of e power j omega 1 x and expectation of e power j omega 2 y. So, this is nothing but the expectation, okay, of so this is nothing but the expectation of e power j omega 1 x, which is nothing but the characteristic function of the x. And here the expectation of e power j omega 2 y is nothing but the characteristic function of the y. Okay, so that is why phi x of omega 1, phi y of omega 2. That means the joint characteristic function phi x y of omega 1 omega 2 is the product of characteristic function of x and characteristic function of y. And the other property is phi xy of 0, 0 is always equal to 1. Product means when both random variables, okay, so are 0, then its characteristic function, okay, will be equal to 1. Next, jointly Gaussian random variables. So, till now we have discussed the Gaussian random variables when they are jointly connected together. So here we are going to discuss about Gaussian random variables. So generally, while we are studying about communication systems, okay, so generally noise samples in different instance, okay, of time are generally modeled as jointly Gaussian random variables. So two random variables x and y are called jointly Gaussian random variables if their joint probability density function is defined like this. So fxy of xy equal to 1 by 2 pi sigma x sigma y square root of 1 minus rho square e power minus 1 by 2 into 1 minus rho square into s. So where s value can be found by using expression s equal to x minus mu x by sigma x whole square plus y minus mu y by sigma y whole square minus 2 rho x minus mu x y minus mu y by sigma x sigma y. So if the probability density function is like this, okay, joint probability density function is like this, okay, so then those random variables are said to be Gaussian random variables. And coming to the properties of Gaussian random variables. So if x and y are jointly Gaussian, then x and y are both Gaussian, but the converse is not true. That means if x and y are jointly Gaussian with the probability density function mentioned previously, so then both x and y are Gaussian, but the converse, that means if x is Gaussian and y is Gaussian, it is not necessary that both x and y are jointly Gaussian. That is the converse. It will not be true. But if they are jointly connected by using Gaussian expression, then the separate random variables x and y are Gaussian. If x and y are jointly Gaussian, then for any constants a and b, the random variable z is given by z equal to ax plus by. Okay, so which is nothing but the Gaussian with the mean mu z equal to a into mu x plus b into mu y, and variance as sigma z square equal to a square into sigma x square plus b square into sigma y square plus 2ab sigma x sigma y for x square. Okay, so this is nothing but the linear transformation. Okay, so of jointly Gaussian random variables x and y. Okay, so if you take one function z and if you apply linear transformation, okay, So on that. So then the resultant values of mean and variances will be like this. Two random variables Rvs, okay, x and y are independent if and only if x and y are uncorrelated. So if rho of x, which is nothing but the correlation coefficient, if it is 0, okay, so then those are known as independent random variables. And here we have one more example problem. Okay, so here we are going to find the joint probability distribution function. Okay, suppose x and y are two jointly Gaussian, okay, 0 mean random variables with the variances of 1 and 4 respectively and a covariance of 1. Okay, so find the joint probability density function fxy of x. Okay, so mu x and mu y is equal to 0. Okay, 0 mean. So sigma x square is 1. Okay, variance of x is 1. Sigma y square equal to 4. Variance of y is 4. And covariance, okay, when they are connected together by using Gaussian expression, okay, then covariance they have given is 1. Okay, so here 0 mean and covariance 1. It tells us the random variables are standard Gaussian random variables. So how to find now PDF value? Okay, first let us find the coefficient. Okay, correlation coefficient. Okay, because to find the probability density function we need rho value also. So find rho xy, which is nothing but the ratio of covariance of x comma y and the product of sigma x and sigma y. So covariance of xy is 1 by sigma x value, okay, 1, sigma y value square root of 4, which is nothing but the 2. So 1 by 2 we have got. And fxy of xy, probability, okay, joint probability density function is defined by using the expression. Okay, so here you can see it properly. Fxy of xy equal to 1 by 2 pi sigma x into sigma y square root of 1 minus rho square into e power minus 1 by 2 into 1 minus rho square into a. So when we substitute the given values and obtain values in this expression, so the resultant value will be of this order. Okay, so that is equal to 1 by 2 pi. Okay, so that's e power minus 2 by 3 x square minus y square by 2 plus x square by 4. Okay, so this will be the resultant fxy of xy, joint probability density function. Next, coming to the transformations of random variables. Okay, a linear transformation is a change to a variable characterized by one or more following operations. Okay, so here linear transformation in the sense here we are changing the random variable. Okay, by adding or subtracting, multiplying and dividing the random variables respectively. So here first one is adding a constant to the variable. Okay, so when we add any constant value to the random variable, okay, so then we can apply one type of linear transformation. Similarly, subtracting a constant from the variable, multiplying the constant by a multiplying the variable by a constant or dividing the variable by a constant. When a linear transformation is applied to a random variable, a new random variable is created. Okay, so whenever we perform these transformations on random variables, so we are going to generate new type of random variables. So to illustrate, let x be a random variable and let m and b are the constants. So each of the following examples show how a linear transformation of x defines a new random variable y. Okay. So here we have taken one random variable x and we are going to apply several transformations on it. So and we are going to obtain new random variable, so which is denoted by y here. So adding a constant y equal to, so x plus b. So we have added constant b to the x and we have obtained the new random variable y as x plus b and subtracting a constant y equal to x minus b and multiplying by a constant. So y equal to, so m is constant, we are going to multiply x by m. So we will be getting y is equal to mx. Dividing by a constant, y is equal to x by m. Multiplying by a constant and adding a constant. So here we are going to multiply random variable x by m and we are adding plus b which is held by the constant and the new resultant random variable is y equal to mx plus b. And dividing by a constant and subtracting a constant and y equal to x by m minus b. Okay. All these are different kinds of linear transformations that we can perform on random variable. So hope you understand this concept and thank you so much for your attention.